So to solve a problem where you have sines and cosines, but different arguments inside, so the argument is wherever you're evaluating, you have to use a product of sum identity. The product of sum identities you may not have seen in a previous trig class. I'm going to navigate away from this for just a moment. They come from, Wikipedia has an overwhelming number of trig formulas. There's a lot. Here we go. They come from the sum and difference formulas, which are pretty much the kind of the first, besides the Pythagorean theorem, the first trig identities you learn, or second trig identities you learn. So you can combine those to end up with the product formulas. So for this problem, we just got to pick the right product formula to evaluate this here. So we have two sines being multiplied. So then we want this one right here. So then we can rewrite this as the integral. We can pull out the 1/2, and then we'll have the cosine of, we'll say this one is our theta, and this one is our phi. So we're going to have a 3x minus 9x. So that's going to be the cosine of negative 6x minus the cosine of theta plus phi. So 3x plus 9x is going to be 12x. Before I continue, I just want to think about this for a second. I have to be a little bit careful with the antiderivatives because of the -6 in there and the 12x in there, because the chain rule would have been active going the other way. So we got to kind of undo the chain rule there. Other thing to consider is the cosine is an even function. So that means if you plug in cosine of negative 6x, that's the same thing as the cosine of 6x. So I don't have to worry about that right there, because cosine is an even function. Right. So again, my point is, because cosine is even, the cosine of negative 6x is equal to the cosine of 6x. Kind of like x squared, same idea. It eats up the negative. We're evaluating this from 0 to pi. So the 1/2 hangs outside. And antiderivative for cosine should be a sine. 6x stays in there. If we took the derivative of the sine of 6x, we'd get the cosine of 6x times 6. Since the times 6 is missing, we have to adjust with a 1/6 for the antiderivative. Similarly, this one will be a minus 1/12 sine of 12x. And then it's just a matter of evaluating it from 0 to pi. So I'm going to get 1/2 and then 1/6 sine of 6 pi minus 1/12 sine of 12 pi. And again, usually I would just jump to the calculator on this one, but I'm going to play a little bit more just for fun. Minus parentheses, to be careful, 1/6 sine of 0 minus 1/12 sine of 0. Lots of parentheses. And since we have pretty nice numbers like 6 pi and 0, we should be able to do this without a calculator. So just for fun, I'm going to try that, and then I'll check with my calculator. Sine of 0 is 0, so these guys are gone. So that's kind of nice. Let's see, sine of 6 pi and sine of 12 pi. Just think about the sine for a minute.
Like 2 pi.
So every pi and 2 pi is a 0. So it looks like we've got a lot of zeros here.
I want to say my answer for this one was 0. So.
Yeah, so we should be able to see this graphically. If we look at this function right here, we should see that its ups and downs balance each other out on the interval from 0 to pi. So let's just take a peek and look at it graphically to see that that's going to happen. Desmos today, and my function I'm trying to integrate is f of x equals sine of 3x minus the sine, or no, times, excuse me, sine of 6x. Going up to pi, so I'm going to graph x equals pi. So we've got part of an up here, and then we have a symmetric down. So those two should, looks like they should cancel out. Let me just blow this up and screenshot it to confirm. On that page, let's put it on a new page. So just visually here, we have a positive area there and there and there. And it looks like we have symmetric negative areas here and here and here. So these guys should cancel each other out, right? Plus, 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 and minus, minus, minus. So that seems like a reasonable answer looking at the graph.